good morning everyone. So in the last class we have seen experiment number 7. So there I have given you demo with respect to Multisim software. So now I'm going to explain you experiment number 8. I'll also perform this experiment here in this demonstration. So please listen carefully. So the experiment is verification of Thevenin theorem and Norton theorem using multisim software. See, um, probably in your basic electrical engineering subject, okay, or else in your subject you might have heard about these topics, Thevenin theorem and Norton theorem. Okay, see, these two theorems plays very key role in simplification of networks. You might have performed these experiments virtually in that basic electrical engineering laboratory. So, so I hope you are having idea. So there virtually in real time you might have been did this experiment here. So my objective is to perform the same experiment in multisim environment. Okay, so the objective is to verify Thevenin's theorem and Norton's theorem using multisim software. So let me ask you a question. So what is Thevenin theorem? Okay, so any two-terminal linear network having number of voltage sources, current sources, and resistances can be replaced by a simple equivalent circuit consisting of single voltage source VTH in series with a resistance RTH, where VTH is the open circuit voltage across the two terminals and RTH is the equivalent resistance across the two terminals with all the sources replaced with their internal resistances. Okay, so here with a diagram I have explained, with a diagram I have shown here. See here, any two terminal linear network with a black box I have shown. So the network can be of anything. Okay, so to that network definitely there should be a load resistance, right? Load resistance means I need not specify. Okay, this itself should be the load resistance in the circuit. Load resistance maybe any resistance through which a current has to be determined, or else the output voltage has to be determined. Okay, so any two terminal linear network can be replaced by this type of network. Okay, so beside to that network you could observe that there is a network in which VTH and RTH are connected in series to each other, to which a load resistance was being connected. Okay, in the classroom environment you might have been learnt how to convert a two terminal linear network into a Thevenin equivalent network. Okay, so of course, even though if you have learnt in your classroom, here in this observation also I have given you the procedure to find out the Thevenin equivalent circuit. Okay, so see here, this is the circuit. So the procedure may be, okay, stepwise I have given here. So I'll explain in detail. See here, first what should you do, sir? So if you are having any linear two terminal network, you need to identify the load resistance. After identifying the load resistance, what should you do? You need to calculate the open circuited voltage here. In order to calculate open circuited voltage, so what should you do? So you should open circuit this load resistance, and then you need to calculate VTH here. VTH means the open circuited voltage across these two terminals. Okay, so beside to this network there is one more network here. You could observe it carefully. This is what Thevenin equivalent circuit is. So if you calculate VTH and RTH here, open circuited VTH and RTH here, then that values, okay, if you replace in this particular circuit, that itself will be the Thevenin equivalent circuit. Okay, so that is what I have mentioned here in this circuit. So see here, I have given you a circuit diagram. In this I have given you a circuit diagram. You could observe it carefully. See here, so this is what the circuit diagram. So manually you need to do it on paper. The space was being provided to you, so you people should calculate, you people should draw the Thevenin equivalent circuit for this particular circuit. Okay, this is the actual circuit. This actual circuit you should convert it into Thevenin equivalent circuit. So I have already did this, so you can see it here. See here, this is the actual circuit. So here this 1 kilo ohm resistance itself will be the load resistance. Okay, to find out Thevenin equivalent circuit, what should I do here? The first step is I need to open circuit the load resistance. So if I open circuit the load resistance, load resistance, the circuit appears to be like this. So here across A and B terminals where you have removed the load resistance, you need to calculate VTH. Since this A and B are being open circuited, you can observe that this particular 100 ohm resistance is flying without any connection. I can term it as it was been it finds no closed path. Okay, so I need not bother about this 100 ohm resistor. If I calculate the voltage across 330 ohms resistor, that itself will be VTH. Okay, so in order to calculate voltage across 330 ohm resistor, okay, so what should I do? So since no current flows through 100 ohms resistor, so there won't be any voltage across 100 ohm resistors. VAB will be equal to V30, 330 ohms itself. So for that what I should do, I need to calculate I1 here. So in order to calculate I1, what should I do? So this will be the total resistance 220 plus 330. So V in divided by 30, I mean V in equal to 30 divided by this total resistance 550 will be giving you I1. Okay, if you multiply this I1 with 330, you will be getting a voltage across this 330. That itself will be Thevenin voltage. So that is what I have done here. The Thevenin voltage is 18 volts. Okay, so the Thevenin equivalent circuit. In order to calculate Thevenin equivalent circuit, I need to determine one more parameter, that is RTH. In order to determine RTH, what should you do, sir? So the same across the two terminals A and B itself, you need to determine RTH. In that process, if you find any voltage sources or else any current sources, any sources, if you find any sources, you need to replace those sources with their internal resistance. So we are having 30 volts voltage source, right? So since it is a voltage source, it may be having an internal resistance of 0. So internal resistance of 0 means it should be short circuited. So here I need to calculate RTH. 220 is in parallel with 330, which is in series with 100 ohms. So if I try to calculate, it will be 232 ohms. Okay, so this would be the Thevenin equivalent circuit. Okay, what is that? This would be the Thevenin equivalent circuit. VTH equal to 18 ohms and RTH equal to 232 ohms. So you have learnt how to calculate 232, I mean VTH and RTH. So let me write down those values here. VTH equal to here you need to fill it. VTH equal to 18 volts and RTH equal to 232 ohms. Okay, so you have got that value. Okay, so now you need to do one thing. Observe this tabular form, all of you. So if you observe the tabular form here, so you are having a tabular form like this. So what is the input voltage? 30 volts. Okay, 30 volts is the input voltage. So here you need to connect this actual circuit there in Multisim. This circuit has to be connected in Multisim. There you need to calculate this voltage V. Okay, so then you need to calculate the current flowing to resistor R. Okay, so you know how to calculate these two. So you need to connect Multisim and you need to determine these values. After determining this, you need to note down this VL and IL in the tabular form. Later on, you need to connect this Thevenin equivalent circuit. After connecting this Thevenin equivalent circuit, you need to determine IL dash and VL dash. So thereafter you need to calculate the percentage error. See how I am doing. So you could observe that there are 4 resistances, right? So you could observe that there are 4 resistances. So how should I connect it? So see here. So go to place. So the procedure already I have explained you. So in the same fashion I am doing. So I need a DC power supply. Okay. So the DC power supply may be 30 volts. Okay. So next one is basic source. Okay, so what are those? resistances. What are the how many resistances do we require? We require 4 resistances. Okay, 4 resistance I am placing, 4 resistances, 4 resistances. So after placing 4 resistances, okay, I need to make necessary connections, right? So for me, to make it legible, what should I do? See here. So for my convenience, okay, I'll be rotating these resistors like this. Okay, okay, see, right. So this alone I'll be dragging like this, this alone I'll be dragging like this. Okay, so this has to be dragged here. Okay, this has to be rotated like this. So later need to place this here like this. So necessary connections have to be done. Okay, so you know how to establish connections. You know how to establish connections. So see how I have established connections. One should not forget to place ground. Okay, so that is very, very important. Okay, so I have made the connection. What should be the voltage? The given voltage itself is 30, right? So I am replacing the value 30. So I have shown you how to replace these values and all. So what are the resistances? So I do remember that 220, 330 and 100. Okay, this is 220. Okay, this is 330 and this is 100. Okay, so I have replaced the values, so you could see it clearly here. So I need to calculate the voltage. I mean, I need to observe the voltage across this 1 kilo ohm resistor. What is the load resistance here? The load resistance is 1 kilo ohm resistor. So I need to connect a voltmeter here, I mean a multimeter. So one more multimeter is required. Okay, so to calculate current, I need to make this multimeter to be operated as ammeter. Okay, this is voltmeter, so I should opt this to be operated as ammeter. Okay, so I'll keep this aside. So for my comfort, I'll be rotating this 90 degrees. Okay, so I'll be placing this in volts. Okay, condition. So to this circuit, okay, I need to save this file, right? So save. So what was the name that I have to give? So I may be giving multi3. Okay, so I'm saving this file as multi3. Okay, I'm saving this file as multi3. So I have saved it. Okay, so to this circuit there is equivalent circuit, right? Thevenin equivalent circuit. Let me see that circuit. Let me show that circuit to you. So what is VTH? VTH is 18 volts and RTH is 232 volts. So simultaneously I'll be connecting that circuit also in the same workspace. So that will be different, of course, no problem. So it is our own interest. Let me see. DC power source. Okay, so I need one resistor, right? 2 resistors I need. So what should I do? I should select basic, then okay, Thevenin equivalent, okay, so close, rotate this to your convenience. So place, do not forget to place ground. Okay, ground should be placed here. Okay, so connect a voltmeter and ammeter. Okay, we'll be specifying this multimeter to be ammeter. Okay, so I need to calculate the voltage across this 1 kilo ohm resistor, right? So for that, this has to be opted to be as to be ammeter. Okay, we should not forget that. Okay, so one more multimeter is required. So so connections were over, so this should be voltage. Okay, these two windows correspond to this Thevenin equivalent circuit. Okay, I need to change this RTH also. What is the value of VTH? VTH is 18. Okay, Thevenin equivalent voltage, and RTH is, what is RTH? What is RTH? Right, it is 232. Okay, 232 ohms. Okay. Right, that's all. Now I need to simulate and verify whether these values are approximately equal or not, and then I need to determine the error. Okay, so this particular meter corresponds to this voltage of actual circuit, and this particular meter corresponds to the current of this meter, I mean the ammeter. So you will be finding IL and VL here, okay, in these two meters. So here you can find out IL dash and VL dash. Okay, so let me simulate. So plus F5 or else click over here. Okay, so see here, you can observe that the currents and voltages are same. Okay, since there is no error at all, right? See here, so the voltage across 1 kilo ohm resistor in the actual circuit is same, I mean, as that of in Thevenin theorem. So see here, the percentage error can be calculated in the tabular form I have shown you. See here, the percentage error can be calculated either by using ILs or else VLs. The percentage error is equal to IL minus IL dash. IL dash means the current across load resistance, current through load resistance in Thevenin equivalent circuit, and IL is the current through actual circuit. Okay, divided by IL into 100. In place of IL you can use VL also. You can notice that the voltage across Thevenin equivalent, I mean the voltage across the load resistance of Thevenin equivalent circuit and the actual circuit is same. Sir, when you are doing this practically in laboratory, you cannot get a resistance equal to 232 ohms. You cannot get. There will be some standard values. If you want to get 232 ohms voltage, the instructor or else the lab instructor will be giving you 220 ohms resistor. So you cannot find 232 ohms. Okay, that may be an advantage of this particular multisim. Okay, so 220 ohms also the same way. Okay. Okay, 1 minute, sorry, 1 minute. So that may be termed as an advantage. So from this, what would you conclude, sir? The error, okay, with the components you may be getting error, but if you use multimeter, multi-sim, you will never get errors. Okay, so that is the advantage, sir. See here, if I wanted to get 232 ohms, 232 ohms resistor in laboratory, it is not at all possible. Okay, by using multisim only it is possible. So practically you may be getting a percentage error, but here in multisim you may not be getting a percentage error, so you need not worry about that particular column. Okay, so hope you all understood doing this experiment. Okay, let me show you how to do Norton's experiment. So you need to fill this and you need to calculate percentage error. Okay, so you need to stop this. After stopping, let me explain you how to convert the circuit into Norton equivalent circuit, actual circuit into Norton equivalent circuit. Okay, and then do the same. Okay, so you can whatever I have did for Thevenin equivalent circuit, you can do it on your own. So I will be giving you as an exercise. I'll just explain you how to convert the given actual circuit into Norton equivalent circuit. See here, this is the actual circuit. Okay, in your observation I'll show you. This is the actual circuit, sir, given for you. So for this you need to calculate Norton equivalent circuit, and you need to define Norton equivalent circuit means what is Norton theorem. Basically Norton theorem is nothing but any two terminal linear network having number of voltage sources, current sources and resistances can be replaced by a simple equivalent circuit consisting of a single current source ITH or else IN in parallel with resistance RTH. Okay, see here the calculation of resistance RTH, and here in Norton theorem RTH is both same, sir. Okay, see here that ITH is nothing but short circuit current at two terminals, and RTH is nothing but equivalent resistance across the two terminals. So I have given you the procedure also to find out the Norton equivalent circuit. Anyway, in your basic electrical engineering you might have been learnt doing this. Okay, so you need to do this in your in the space given in the observation. So you need to determine IN and RN. So you need to connect the actual circuit, and you need to determine VL and IL as usual what you have done in the Thevenin theorem, and then to the Norton equivalent circuit to this actual circuit you need to determine IL and VL also. So you need to note down the values in the given tabular form, and you need to determine the percentage error. So I have shown you, I will show you the procedure. See here, this is the actual circuit. To calculate RN, the procedure is same as the procedure used to calculate RTH in VT, Thevenin equivalent circuit. Since the circuits are same, the RTH, I mean the open circuited resistance will be same, that is 232 volts. My objective here is the only prospect here for me is to calculate IN. So IN is nothing but short circuit load resistance. Here there in Thevenin theorem what you have did, you have open circuited this load resistance and you have calculated VTH. But in Norton theorem, so you need to short circuit this 1 kilo ohm resistor. You need to take off this, you need to short circuit this 1 kilo ohm resistor, and you need to calculate IN. Okay, so if you short circuit 1 kilo ohm resistor, the circuit appears to be like this. Okay, so here I need to calculate IN. Okay, so for that I need to define IT, right? IT. In order to define IT, here I need to define RT. RT is nothing but 100 ohm parallel to 330 in series with 220. So the RT value will be 296.7. So if you try to calculate IT is nothing but Vin divided by RT. The value will be 0.1010 amperes. Okay. So IN by using so you got IT, right? You got IT. So by using current division rule. So current division rule means if you wanted to calculate a current through a branch, okay, so it is given by total current multiplied by opposite resistance divided by total resistance, sum of these two resistances. Here the opposite resistance can be 330 ohms. Okay, to calculate IN equal to IT multiplied by 330 divided by 330 plus 110. So that is how I have calculated IN. So I will be defining this Norton equivalent circuit. See, as whatever I have done to Thevenin theorem verification, the same thing you need to do it in the Norton verification also. So see here, the actual circuit you need to connect in Multisim software, and you need to connect the Thevenin equivalent circuit, Norton equivalent circuit, and you need to check whether the current through the load resistance and voltage across the load resistances are same to that of equivalent circuits. Okay, thank you.